Hey everyone, welcome back to my channel. In today's video, we're going to look at the problem I gave you in the last episode, that little bonus I left you as a homework. And we'll go step by step through the solution and then dive into something deeper. We're going to discuss what is the difference between Bayesian and frequentist approach in the probability theory. We will also talk a little bit about the philosophy behind the probability theory and how these ideas like epistemic and ontic knowledge and uncertainty fit into the grand picture. So yeah, there are lots of interesting stuff today, and without further ado, let's get on with this. I hope you all tried solving that problem yourself, and I hope you found the answer. The result is actually counterintuitive. The answer to this problem is 1 out of 3. The probability that in a family with 2 children, at least one is the girl. The probability that both are girls is actually 1 out of 3. This result is profoundly counterintuitive. The common sense tells us the sex of one child is independent of the other, and knowing that one kid is a girl, the other child still has 50-50% chances of being a girl. And this intuition, of course, logical, but it is based on subtle misinterpretation of the problem. The first thing that you have to understand about the probability theory is that it is essentially the game of valuable information. Well, in most cases. We're going to discuss this in more details a little bit later. Now let's try to focus on this problem. What is the sample space for the given problem? The first thing we have to do to avoid the flawed intuition and the common biases and the common errors, we have to outline the sample space. In our case, we have the girl and boy, boy and boy, boy and girl, and girl and girl. This is our sample space. And what is important here is that the order of our children actually matters. That being said, our boy and girl and boy are 2 different possibilities. And then we have a new evidence. We have the information that at least one of our children is actually a girl. That being said, our sample space can be reduced to only girl and boy and girl, and girl and girl. There are only 3 possible outcomes left. Before any of this information is provided, each of these distinct scenarios in our first sample space has a 1 in 4 or 25% chances of occurring. This 4 outcome set is like a baseline or prior state of our knowledge, just called the prior knowledge or state of the knowledge. But the failure to distinguish between this girl and boy and girl as 2 separate probabilities and instead lumping them into one single one of each category is the primary source of confusion here. This is called intuitive error. So that highlights an important point in probability theory. Probability theory can be considered as the study of valuable information. And this interpretation of probability theory is called a Bayesian interpretation. In the Bayesian worldview, probability is not an objective or physical property of the world, like mass or temperature. Instead, probability is an epistemic state. What that means, it is a quantification of a rational agent's degree of belief or a state of knowledge. Or in other words, a rational subjective plausibility. In the context of this interpretation, we are all just agents, like you and I, or any other machine, or artificial intelligence, or anyone else. Maybe even an alien on another planet. It doesn't matter, because we're all agents. And what the agent has is the scope of valuable information and the proposition. The information is also called the evidence. In our case, what kind of valuable information we have? This is our first step. We have a sample space. We have valuable information that we have 2 children and we have some kind of order between them. One child is older than the other child. For example, the girl is older or the boy is older, it doesn't matter. But we have some kind of order between them. So in our valuable information, in our state of the world that we have, this is our small world, our model of the world, our sample space. We have 4 possible outcomes. And then follows the filtering step. The filtering step is when we're filtering out possible outcomes with the new provided evidence, because we gather new information from the world, and now we can use this new information, new evidence, to reconstruct our model or interpretation of reality. We can reconstruct or modify the model or interpretation. And we did so. In our case, we excluded the outcome when both kids are boys. We don't need them anymore. We were provided with information that at least one is the girl. And in this case, the probability that both kids are actually girls is 1/3. It is this exact outcome. So what is the Bayesian interpretation? This is exactly what we've just done. This is using valuable information and gathering the evidence to form a new, and this is very important, subjective probability. Why subjective? Because it is based on our belief. It is based on our state of knowledge, on the amount of information that is available at a moment in time. It can change over time because we are getting new evidence and new information. And the other very crucial thing here is to apply probability rules consistently and using a very consistent logical framework and logical rules as probability theory to generate new knowledge. That's why our agent, our subjective belief, is called rational. It is called rational because we're using consistent logical rules applied to the amount of information available to us to make an educated guess. In our specific problem, the family itself, the physical reality, it never changed. But what changed here is our state of knowledge. The probability is not in the family, is not in the physical reality. It is in our model of the family, in our interpretation of the world. So the game here, the probability here, is like the process of updating that internal model, interpretation, representation of the reality as new information becomes available. Bayesian reasoning is thus a continuous learning process. It is the formal logic of how rational agents and modern artificial intelligence, or we, for example, learn about the world. We start with initial belief, a prior knowledge. We encounter new data, the evidence, and we use that evidence to produce an updated, more refined belief, a posterior belief. And this is the very essence of game of valuable information. And this is called irrational because we are using the consistent formal logic or consistent probability theory. Consistent rules. We apply the consistent rules of logic. And sometimes we may even derive a new knowledge within the framework itself and based on the prior knowledge. This is called rationalism. I'm not going to talk a lot about rationalism here. To put it bluntly, this is the essence of Bayesian reasoning. So the Bayesian reasoning and Bayesian interpretation of the world comes down to the question of epistemology, the nature of knowledge, rather than ontology, the nature of reality. The Bayesian answer to the probability is that the probability is the fundamental logic of reasoning under uncertainty. You may be wondering, there must be another view, must be another interpretation on the probability theory. And you're not wrong, there is. To fully appreciate the Bayesian reasoning in the mind interpretation, there is another one which can be put in the contrast. And this philosophical rival is called the frequentist interpretation. The frequentist view posits that probability is an objective or physical in the world property. It is not just a degree of belief. It is defined as the long-term relative frequency of an event, which would be observed given theoretically infinite number of repeated trials under essentially identical conditions. For example, saying a fair coin has a 50% chance of heads, from a frequentist perspective, it is not a statement of belief. It is a statement of physical effect, meaning that if one were to flip that coin infinitely many times, the ratio of heads to total flips would mathematically converge to 0.5 in the long run. This is the interpretation what underpins much of the experimental science, where we run repeated experiments to discover these objective frequencies. So that's quite empirical. But from the Bayesian perspective, we still have a 50% of heads, but not because we have some empirical observed frequency of coming up with a head, but because we have the uncertainty of our knowledge. We don't have a knowledge about the initial forces, air, gravitational force, or any other parameters that could potentially tell us if we have a head or a tail in the outcome. So we're highly uncertain here, and we just say there are two possible outcomes, and for this reason, we don't know the answer. We're just gonna go with 1/2. That's the Bayesian framework. We're not conducting any empirical data here. We're not conducting any experiments. We're just saying we're uncertain, and that the probability 1/2. Two main interpretations in probability theory that can be applied when we are solving real-world challenges or mathematical problems like this one with two-child. So what would be the reconciliation between those approaches? Well, honestly, those two approaches are not in a conflict. They are partners in a continuous cycle of learning. The frequentist data from the objective world, the one that we are observing in long-run frequency of experiments, is exactly what informs our Bayesian prior knowledge. So we are using this knowledge, and we are using these objective frequencies from the world to build our subjective beliefs, which we then update with new evidence. So they complete each other, even though at the first glance, they might seem very contradictory. These two interpretations are cornerstone of modern probability theory, and they complement each other. In that case, one may be wondering, does it even make sense to rely on probability? If the probability is so uncertain, if that's just a subjective rational belief, or how it is called, rational subjective plausibility, can we even trust to the probability theory? Well, the alternative to formal probability is just not certainty. It is the flawed intuition. It is the cognitive bias, the systematic error. Probability theory is actually not ideal. It is not a crystal ball that will tell us what will happen. But what it does, it is the optimal and the only possible framework for making rational decisions when we do not know what will happen. This is the logical system which provides us a consistent framework for making educated guesses. It is the language that we have invented to manage the uncertainty, and it is extremely useful and very consistent. And this abstract mathematical framework, it is not just a game of valuable information. It is the concrete and invisible bedrock of the modern world. Now let's get to the tale of two uncertainties, epistemic versus ontic knowledges, or uncertainties. What is the epistemic uncertainty? Well, this is also called lack of knowledge. This is the uncertainty of the classical world. It is the uncertainty due to our ignorance, due to lack of information, lack of valuable information. For example, if you flip a coin, we use the probability 1/6 or 1/2, not because the die is fundamentally random, not because it is the inherent property of reality itself, but it is because we lack the knowledge of the precise initial forces, spin, and air resistance. But if we had a supercomputer with all the data, we could, in classical physics at least, predict the outcome with 100% certainty. This is just the game of valuable information that we have been discussing so far. There is another side of the coin, the Ontic uncertainty. It is also called fundamental indeterminacy. It basically states that reality itself is indeterminate at the quantum level. It's not about our ignorance or lack of information or valuable data. It is a statement that reality itself is fundamentally indeterminate and uncertain. For example, if you have an electron before it is measured, according to the quantum theory, for example, it is not just a single location, but we just don't know. It fundamentally doesn't possess a definite location. So this is not a game of valuable information itself, because the information doesn't exist to be found. But what is happening when we try to apply our epistemic tool, the probability itself, to our ontic reality? If our probability framework and lack of knowledge confronts the very fabric of reality itself, is there any process of reconciliation? The answer to this question is that the universe, while fundamentally uncertain, it is not chaotic. Its uncertainty is governed by the exact probabilistic and physical laws. The most important of these laws is, for example, the Born rule, and central postulate of that is that quantum mechanics that connects the ontic reality and fuzzy reality of the universe to the epistemic probabilistic predictions we can make about it. For example, if I have a particle like an electron, which is described not by the position, but by a mathematical object, which is called the wave function. This wave function is its fuzzy ontic reality. It describes all the particles, potential locations, and momentos at once. So applying the Born rule provides us the key. It states that square of the amplitude, the height of the wave function, at any given point gives us the probability that we'll find the particle at that point if we perform a measurement. To put it simply, it basically says, yes, there is a fundamental uncertainty of reality, which is ontic, and there is epistemic uncertainty, the lack of knowledge itself. So what this Born rule means is that we can basically apply our probability theory to our ontic reality using a mathematical framework and make educated guesses about the reality itself. It doesn't mean that we know the location of the object. It doesn't mean that we can say for sure that this event will happen, but it means that we can apply our probabilistic mechanism or our framework to get the estimation of the plausibility of the specific event. That being said, we can always apply the mathematical framework, mathematical tools, or epistemic uncertainty tools to get more insights, more information about the universe itself, even though this universe is uncertain at its core. So that's sort of reconciliation between two uncertainties. Thus, the probability is revealed to have the dual-natured concept. It is the epistemic language that we use to describe our own state of knowledge, and at the same time, it appears to be the ontic language in which the fundamental laws of the cosmos itself are written. And this is the most fascinating thing about the mathematics, and how it reflects the reality itself, and how it can be applied to describe the universal phenomena, which I myself found really fascinating. And in the next videos, we're going to continue exploring more problems like this one to reveal even more details and intricacies of the probability theory and discuss them in more detail. And if you really enjoyed that, don't forget that we have our own Discord channel. You can find the link in the description section below. Feel free to join us. It's a chill place to discuss the problems, share insights, and get feedback. And thank you for watching. I'll see you in the next one. Bye.